Okay, hello everyone. Welcome to the first Nebula Graph online meetup. My name is Johan. I'm currently a Nebula Graph database engineer, and today I want to introduce how Nebula works. Okay, you can see. Put the camera closer. So, in here, if you have any kind of questions, welcome to go to the Nebula Graph forum. And in here, you can contribute to our database, or you have some anything that error in your database scenario. Welcome to ask any kind of questions. We usually respond to them within 1 day or 2 days because we have on-call engineers in here, and I really appreciate that if you pose your questions in the forum rather than different kind of other scenario, because it helped other people to see the question and which helped us to solve them together. And I will adjust the workflow. Okay, it was fine. So today's live show will be divided into 5 contents. The first content is, in the first content, I will introduce the graph database and the graph patterns. And then I will introduce about how our database was designed for the graph database scenario, which is mainly for the system design opinions. And finally, I will allow you to ask some questions in the forum or in other kind of YouTube lives or things fine. Before we introduce about graph database, I want to introduce graph at first. So for the graph, here we can define anything in two problems. One is for the identities, which you can also represent them as nodes. And the second one is the edges. Edges is for the interrelation relationship between different kind of identities. And the graph itself is a set which contains both nodes and edges. So you can define you and your friend's relationship, such as friendship, as relationship. If your friend borrow you money, you can find that. So do they have any response? Can you see my talk? Beautiful, strange. Okay. Okay, and if you buy some product, you and your product build some relationship. That is to you. That is to use. That is just like you borrowed some product, or you buy some product, or you buy some content. In such a way, you can define problem in a natural and easy way. But graph problem arose for thousands of years ago. But how we can store graphs or how we can analyze graphs is a big question. And in general, at first, people do not solve them well. That is how SQL do to solve the interconnected data problem. So in a traditional database such as SQL or MySQL, we define schemas to represent data and their interconnected relationship. And in the schema, we will always define IDs to track different kind of correlationship between one schema to another schema. So, but the relationship in the schema do not explain explicitly. That is a simple example. In here, we have 2 tables. One is employee table and one is department table. If we in the employee table, we can define the employees' names and the department ID. And the department table, they have department ID and the department name. However, if we want to connect both of them, we need to at first get the pointer from one employee entry's name, that's Jones, and the department ID, and then use the ID to track the department name, which is located in department table. And then once we found that the department name is engineering, we can connect both of them into one big table, which have Jones and engineering together. That is the basic syntax for such operation. Here we select their properties from department and employee, and then join them with a department table by their department IDs. After the join operation, we can easily produce such a SQL table which contains both of the informations. So join in here play a critical role to find the interconnected components, and join in the traditional SQL have a lot of optimizations. That's the main reason for that is join itself is not a free launch. The join operation happens in SQL it's basically like the join operation happened in sets. So if we have two sets named A and B, we can find that the join can represent some elements that both belong to A and belong to B. In traditional SQL, we define join by the common element that is ID. We use ID to connect the different kind of tables. However, such an operation will cost much more time than you thought. For example, in here, join basically have two kinds of algorithm to represent both of them, such as sort merge algorithm. That we need to sort the element from A and B by keys, and then increase them one by one. The time complexity for sort merge algorithm will cost O n log n is the length of maximum between A and B. And another kind of algorithm is hash join algorithm. Generally speaking, that is to put one set element into a hash table, and then loop over another set to find the current components and get the join set. The time complexity for hash join will cause O(n) time complexity. Besides, for the huge number of time complexity requirements, we also need to seek the join components into different kind of database partitions, which means that there will be a lot of time for internet communications. So you may do not have some sense about the number which is based on how data are interconnected or how different kind of network components are affected together. Here, I personally recommend you to read about Jeff Dean's 10 numbers about every programmer should know. Here you can check them in Google, and I do not show that. To be a more concrete case, for these requirements, such as find all of the direct reports from employees and count the number of reports up to 3 levels down. That is a friend-to-friendship query, and such a query may require you to find all of the direct report from your employee, and then sum over the employee's direct report, and then combine them all together up to 3 levels. For such an application, you may find that the time for such a query will go exponentially when the levels goes up. You can find that you can find the basic benchmark results in here. Besides, not only the performance consideration for join operation, we also need to consider about the debugging complexity and some kinds of implementation complexity for massive amount of join operation. You can find something in the review on graph database. In here, I wrote about 200 lines of SQL to represent such a problem. Besides, for the codes for reciprocal query and join operation, the traditional SQL also do not support for reciprocal queries. So in here, if we build a table based just represent the relationship between managers and their managers, In here, you can find that if we want to find the relationship between employees and their managers, we cannot find them into a single way. That is because of the nature of database design. In here, ID can represent from one to another, but that is not bidirectional. So reciprocal query require a lot of resources to look over all of the database and then find the manager for one certain employee. That cost is usually unacceptable. Plus, for SQL database, there is no way to find to find a pace or the shortest pace or any other kind of graph traversal or graph search or graph clustering algorithm based on naive SQL-based implementations, except for some brute force one. Brute force one will always cause the exponential time complexity, and basically you should never consider them. Graph, that is the reason those three restrictions happened in SQL database. It's the main reason why graph database is born for. Graph database itself is born to solve the graph storage and graph computing problem. How do graph solve them is majority by defining explicitly on the each property. Each property represents relationships, and that is the main difference between graph database and other kind of databases. For, for example, in here, that is a graph database. In graph database, we create tags for different vertex, which defines the vertex attribute, such as person have the name, department have the ID and the name. And then after we define about vertex, we define the work for relationship, which represents some people work for different kind of department with their job titles or holiday or payment information. And once we define those things, we can easily build the table for such a solution. In here, graph database not only optimized for recursive query, which I will introduce later in system design, and it also Nebula Graph itself also optimized for reciprocal queries that we will also introduce later. Besides, by defining both the node and the edges, we can easily solve path problems such as path search, shortest path, or find all paths from one node to another by just one simple query, which is supported the Nebula Graph. You can check on the query commands in our docs here. So in here, if you click on the query language, and then you can find that the graph algorithm supports. Currently, we only support for the shortest path finding algorithm and the path finding algorithm. If you want something more more specific or much more harder, you can create one yourself, or you can expect the Query Engine 2.0 version. In here, we will implement a much more diverse graph query algorithm in here. After we're talking about a lot of scenarios about what the region graph database may have much more higher performance, and how the graph database can represent about graphs. Here I want to introduce about several kind of typical scenarios for you to use graph database. Generally, you can divide the scenario to three general categories. That is social network, recommendation system, and the graph algorithms part. So for the social network part, you may have some links, and you have links, and if you want to find other people's, maybe that is your third connection or second connection. Here, you may build a path from you to your connectors, and from your connectors, you can find the connectors, and to recursively to find the relationship between you and another one. So it is okay if the whole networks have only thousands of vertex or millions of passes. If you use SQL in here, I think it is fine. However, if your network go exponentially, or if you have 1 million nodes or 1 billion nodes in the general case, in here you should consider about performance issues. And then for such a big query, for such a big data set, you should consider to use graph database for interconnected data. The second use case is for the recommendation systems and fraud detections. When the customer want to buy something, they always seek for the shop's recommendations. But how do our recommendations build for? They may build for something like the user's previous orders or the user's preferences or user's browsing history, and based on those kind of things, they can build a relationship. Based on those relationships, they can build some kinds of recommendation algorithm and recommend certain products to the target user. So the analytical part may just restrict the time to a really short timestamp, and performance is critical to let customer to buy what they want and to increase the conversion rate. Plus, for the fraudulent transaction part, you may want to know the person's interconnection between different kind of banks or different kind of other laundry system or other things to find whether the transaction from one people to another people is fraudulent or not. Okay, plus for the recommendation system, if you want to use graph algorithm in your dataset, you can also seek for the help with graph database. In here, graph database, such as for critical connection problem, which you may find the node or the path which is the most fragile to the system, and once the node or the path failed, the whole system will not be connected. So if you want to find such a path into a really complicated graph, you may seek for help of the graph algorithm, and you may store their data into a graph database. Or if you want to find some other kind of thing, such as graph clustering problem, to find the user which have some kind of user preferences, you can use graph algorithm in the graph database as well. Here is a case for real life. You can check for the link for the much more diverse slide. In here, Netflix used their cloud database to store the digital assets information about and to manage different kinds of digital asset identities, such as movies, display sets, and so on in here. And the relationships in here is to build up different kind of assets. So every day there are 2 million nodes in the cluster and hundreds of queries or updates per minute, and it is allowed to run them in real life. After talking about what is graph database or when should we use graph database, in here I want to introduce about the Nebula Graph system design. The main purpose of our system design is focusing on how to make the graph database become scalable and available. That means that we can easily increase the performance or increase the graph storage capacity by adding more machines or adding more hosts without worrying about the performance restrictions, which may be hampered by the leader node or other things or suffer from leader failures. All of those things you should not be worried about our system design. Plus in here we also support for we both support for high parallelized the query engine and high parallelized the storage engine. And both storage engines are supported for graph kind of consensus to support fault tolerance and replications. Each part I will introduce them into pieces and talk about their trade-offs for the graph scenario. So the query engine part is the main part I'm engineering for. In my work, I researched on use LLVM just-in-time engine in the query engine part to optimize for the physical plan. So in the first part, I want to introduce much more specifically about how query engines work. In general, if we have a Nebula feature that is in here, let's use just like find the people whose name is Jeff. So in here, that is a simple query. Rather, that is the how human reads about their queries, but not how machines read about those queries. Machines generally run query into several parts. And firstly, it will run lexer and parser. Lexer itself will decompose queries into different kinds of tokens, such as in here, it will be passed by the spaces or by some special characters. And then parser will parse different tokens into expressions and pass to the logic plan, which allow us to build a logical abstract syntax tree for the physical and concrete implementations. And for the physical plan layer, which we can do a lot of things, such as support for CPU and GPU, or support for the JIT just-in-time engine, and so on to help us to get better performance. In Nebula itself, we currently only support for CPU, and you can expect for more features. And after the physical engine part, we can go to the optimization part. Optimization will do a lot of things to so that the query time becomes shorter. But for the one thread query operation, the computing time will not always be satisfied. So we also support for distributed query engine and distributed executions, which means that you can run your queries into parallel and use Kubernetes and protocol buffer to communicate between different kinds of query engines, metadata services, and storage engines, which also make it possible to do load balancers between different kinds of storage engine and their loads. I personally recommend you to know about a graph database by such to know about graph query engine by doing some work which is done by LLVM. In here, you can implement a simple compiler based on the here it is a basic compiler for some simple grammar operations. But after you implement all of the things, you can know the basic concept about how the compiler works, and that is just the basic fundamental knowledge about how query engine works. I also recommend you to check on some kind of open source query engine part, that is Ballista. In Ballista, it's supported to use Apache Arrow to communicate with different kind of query engine in a unified way. Plus, it can support it have done a lot of optimizations in the physical layer, such as it supports for parallel computing, and it also supports the distributed computing, and it is implemented in different kinds of languages, such as writing in Kotlin or writing in Rust. So after you review those kind of algorithms, you can get to know about query engines much more easier. Okay. So after we all, the distributed query execution is pretty. It's not a free flow. I need to mention at first, because of the nature of the distribution, which will introduce overhead to synchronize different kind of loads. It works pretty well on the long tasks, but for short tasks, I think one query engine works well. So after I introduced about the query engine designs, here I also wanted to introduce about the storage service design. In the storage design, at first you need to build some knowledge about the meta service and storage clusters separation. Interservice itself store different partitions, key ranges, and numbers, and the different partitions will use graph as the consensus protocol to help database replication, which is critical for the system design. And I will show you the basic ideas hidden in those designs. So when we want to design the distributed system, the first thing to consider is to consider about scalability and performance part. Whether we can increase machine based on when we increase much more nodes or add more compute resources. It is not the same thing you happen in a single PC, in where if you add much more disks or add much more memories, you can easily get some performance improvements. However, in distributed database, we need to let different parts of things to store in different components. That is the basic concept of partition. In partition, just like to use in partition, there are two kinds of partitions. One is horizontal partition, and another one is vertical partitions. For the horizontal partition, it is also named as sharding. So the sharding part in here is to distribute different kinds of database entries to different nodes based on some certain rules. Another kind of partition is vertical partition, that is just separate things based on the column, which is seldom used in system design, and I will not introduce here. So how to distribute those entries have basically three kinds of ideas. One is range partition, that is used in Cassandra or is used in the HBase, which is used their values as the key to partition them based on their values. For example, in here you can partition the number range from 0 to 3 to one node, and from 4 to 6 to another node, and put the rest into the third node. Range partition itself is okay for some applications, such as you need to stat about the people's name, or you need to stat about other things, because everything can be distributed evenly. But if there are things which stick in one kind of range, or if you want to expand more machines, you will suffer from the migration problems. And if you want to do aggregation queries for a large range of objects, you may need to seek for another different kind of partition number, which will cause a lot of time and latencies. So in here, we introduced another kind of partition, which is a hash partition. Hash partition itself do not support for aggregate operations well. That is because in hash operation we cannot know exactly we cannot guarantee that every kind of query in the range can be distributed into one partition. And once we add more machines, hash partition will suffer from the data migration problems as well. And a consistent hash problem is born to solve this problem by doing a large circle, and then once you add the machine, you just need to migrate one part of them. Nebula Graph itself uses hash partition. That is because we can build the table at first to define how many partitions we have, and use them to do partitioning. So there is no need to add much more nodes in here. Besides, for the partition part is mainly focusing on scalability and performance issue. So, but it do not talk anything about fault tolerance or something named or something that you can keep your distributed system run once some nodes are failed. Those things is the responsibility of replication services. For the replication services, you can that is simple. You can simply understand them as to distribute the data of nodes to different kind of machines. And once the node fails, they can recover the nodes from other machines to restore the data. And one of the most famous architecture for such a replication is master-slave architecture, which is mainly used in MySQL operations. Master-slave architecture, to be a simple way, is that master will handle all of the write operations, and a slave will handle all of the read operations. Their communication can be separated into two ways. They focus on different kind of purposes. One is synchronized replication, which means that master will wait until all of the slaves have already finished their write commits, and then master will say the commit was too dated. Such a replication will wait a lot of time to maximize the latency. And so here, the pessimistic replication do not support for the real-time tasks. So there arises another kind of replication that is optimistic replication, which will communicate between different nodes in an asynchronous way. So once master sends the replication command to different kind of followers, they do not care about whether the followers need to commit their write commits and do write commits again and again. In such a way, they can optimize for the latency time, but they cannot guarantee that every data is up to date. So if you read from the folder, you may read from something outdated data. Both of them cannot satisfy the requirements for our database. And besides, for those trade-offs, the master-slave architecture also suffers from the master node failure, because once the master node fails, they need to re-elect some masters from the followers node. And basically speaking, master-slave architecture do not know about how those things are happened, so it will cost a lot of time. Sometimes if we do not find them, it will cost days or to find that the server goes down, which is not acceptable. So in here, there arise different kind of replication, that is quorum-based replication, which is aimed to find a mediate way for optimistic replication and pessimistic way replication. So at first, in here, I will define quorums. Quorum is the majority part of the system. You can think that it is greater than half of the node, which is in all of the nodes. For example, if there are three nodes, you can say quorum have two nodes, and it will be a more mathematical way if the quorum of the read quorum number and write quorum number satisfy those two constraints. We can say that it is a valid quorum for the database system. And by defining the quorum, we can use quorum duplication to get things done. So in here, the quorum-based replication is finished by something named consensus. Consensus is the most hard part, in my opinion, for the database system, because of the historical reason of consensus is the tactile protocol, which is really hard to understand at first. And after several years, Stanford developed an algorithm named the Raft algorithm. In here, people start to decompose the consensus into several different kinds of strings. If you want to know more about the Raft protocol, you can check on the official website, which is made by Stanford. In here, you can see the leaf show about how Raft works, and you can synchronize the times in here to see that how graph is used the logs to do replications and to do leader elections and how to use them and then how to do the quorum to get the most up-to-date data and how to they synchronize. And for the graph database, we use graph is used. Graph is majority used in several different kind of parts. The first part is okay. The first part is leader election. For example, uh, in the replication part, graph is used to elect a leader once a leader fails. And the leader itself will broadcast the up-to-date information to all of the further nodes to get replicated. And once they found that the majority of their followers get up-to-dated, they will send the success information and then update itself. By doing it, we can always guarantee the strong consistency which is made by graph itself. We also use the graph to do leadership election. So for the leadership, for the meta service part, it is not a simple node. We can build a meta service cluster to increase the fault tolerance behavior. Because in here, we will select a leader for the main data replications, and once the leader fails, we can use that to re-elect a leader. That is the basic knowledge that I think if you want to know about storage engines, you should know about. That is the minimum requirement. And if you want to know further about the Raft protocol and their basic implementations, I personally recommend you to read the source code of etcd. etcd itself is internally used for Kubernetes for strong consistency guarantees. And you can check on the unit tests and the Raft protocols. In here, you can see different kind of things and how the Raft being tested, or how do they use that Raft to handle with the real scenario. I personally also recommend you to read about to do the homework, which is in the MIT distributed system course. In here, you can see you can write a distributed key-value store based on that protocol. So after talking about those things, we can now introduce about how Nebula Graph is partitioned and get replicated. Before I introduce about how Nebula gets partitioned, I want to first introduce about the memory models, which is in the Nebula Graph. So for the memory model, we present nodes into several parts, and I think the most important part is for the vertex ID. For edges, they have two vertex ID, and we have two kind of edges. One is the incoming edges to a node, and one is outcoming edges from a node. Both of the nodes and edges are partitioned by the hash value, which is the merged value from the vertex ID to the number of partitions. By doing it, we can guarantee that nodes and edges which belong to the same node, both in and out edges, will belong to the same kind of partition. So it will be perfect for path-related queries because we also need to find the relevant passes from one node, and we do not want to use to research different kinds of partitions. Plus, once we created an edge from one node to another, we will automatically create another edge, which is from other node to itself. So by doing this way, we can optimize the reciprocal query. So people do not worry about their schema designs, which may not suit for reciprocal queries, because Nebula Graph itself will doing the reciprocal replications at first. So by doing those things, you can say that different kind of partitions will also support for parallelization and support for scalability. So the partition part is important. The another important part is, I think, is shared nothing architecture. Mm, Honestly, that is a really popular architecture for today's system design. In here, you can understand them as a separation from stateless and the stateful components. So, as we previously mentioned, that query engine part is stateless, which means that query engine doesn't know where to execute their queries, well, where to find their queries. All of them are scheduled by the meta services. So meta search itself will store the partition information, and it will also support for the scheduling part for the query engine. Plus, for the upper application, for the storage application, the shared nothing architecture will define as the stateful operation to as stateful objects as different kind of partitions. And the different kind of partitions will build a raft clusters. So for example, in here, partition 1, which is located in 3 different kind of machines, will communicate in the raft protocol. So once one node fails, those are the rest of the 2 nodes were responsible for the database communication and works well. And once they recovered, they can easily find the replicated partition by the meta-series scheduling and by the raft consensus. For the reason why we do not want to use one simple raft for the whole system is that such a thing will demand a lot of resources for the leader and restrict to the performance of the leaders node, which is not good for the scaling problem. So to add the parallelization property and to add much more kind of things, we decided to use the meta service part. Partition itself do not know the information about other nodes, which means that you cannot say that I do not find the key in partition 1, so partition 1 can tell me about where to find the key, where the key located. So all of the things are told by the meta service part, which means that the partition itself have no information about the different partitions, which makes it possible for we to stack the raft into multi-raft protocols, which means that different kind of partitions will build their own raft clusters, and which is optimized for parallelization and performance. As the benchmarking results show, which will be released later in May, we can say that we are at about 10,000 TPS for the current graph database scenario. Okay, that is all. So, do you have any kind of questions? Um, you can check on the Nebula Graph's design and source code in our GitHub link, and follow us on Twitter, or you can join our Discuss forums, which I have already shown in the at first, right? So, is there any kind of questions? Okay. One problem is, let me check. So, wait for a minute. So somebody asked about the benchmarking things. So for the benchmarking things, I think you can wait for the 1.0 Nebula Graph release. That is in the late May, and check for the updates by following us on the YouTube or on the GitHub or other things. And it is unavoidable to compare the Nebula Graph database with Neo4j, which I can assume that is the most famous one for graph database computing. It is true that Neo4j have not a lot of applications and adopted in many industries, such as in Microsoft or in eBay. But the main design purpose of Neo4j is quite different from Nebula Graph. That is, the majority is that the Nebula Graph database is majority optimized for scalability and performances. However, Neo4j is optimized for different kind of purposes. So the third question is there any kind of graph algorithm supported? As I have already mentioned about, the graph algorithm currently supported is basically about path finding and shortest path problems, not for different kind of problems such as critical connections or other problems. It is okay if you want to commit on much more kind of graph algorithms. And you can also expect some more updates about Query Engine 2.0 version. In here, we will implement much more graph query algorithms for you. So I think today's lecture is fine, and thank you for listening. Bye.